I'm sorry that the solution for meeting number 2 will be available tomorrow afternoon. So I will send an email to you, and so you can go to my laboratory tomorrow afternoon to pick up the solutions. Okay, so we have talked about Lorentz series in the first section, and we proved that for any analytic function in an open set, it is representable by Lorentz series expansion. Okay. Now, before we have further results, I will talk about singularities and the zeros in this second section. So first of all, about singularity. Okay. All right, so we say a complex function f of z is said to be singular or to have a singularity at the point z equal to z0 if f of z is not analytical. Perhaps not even defined. Okay, at z equal to z0. Okay, so it's possible that this function is not defined at the singularity, the singular point z equal to z0, or if it's defined but not differentiable at that point. Okay, so right, so this is the first. So it's not analytic at z equal to 0, but every neighborhood of z0 contains, all right, points. All right, so contains points at which f of z is analytical. Okay, so there are two conditions to have a singularity at a point. The first one is that at that point, this function is not analytic. The second, even though f is analytical at that point, but in every neighborhood of that point, there is a point that f of z is analytical. Okay, right? So you have to identify such singularities, and now a singular point c of 0 of a complex function is called isolated and if f of z is analytic, okay, in the neighborhood of z0, except right at the point 0. Okay, and so we may take a couple examples. First of all, tangent C, okay, has isolated singularity. All right, at Z equal to mass plus pi of 2, mass plus 3 pi of 2, mass plus 5 pi of 2, etc. Okay, so in the complex plane here, okay, so we know that we have okay, so that so the cross point here are single points of tangent z. Okay, and for other points, that the tangent z is analytic. Okay, and they are isolated because you can find a neighborhood for every single point. So for here, you can find a neighborhood. You can see. Now in this neighborhood, so this is the disk of pi over 2. Okay, and so this is epsilon here. So in here, that if we remove the center, then we have punctured the disk, and we see that the tangent z is analytic. Okay, in here. Okay, so the tangent z in this punctured disk, that tangent z is analytic. Okay, so and but at the point z equal to pi over 2, you see that f of z is not defined there, so of course it's not analytic. Okay, but every neighborhood of z0 contains points of that f of z is analytic. And for all other points except the center of this disk, tangent z is analytic. Okay. So we have an isolated singularity here. But if we consider this complex function tangent of 1 over z, okay, then this function has a non-isolated singularity at z equal to 0. First of all, you can see this function is not defined at z equal to 0, of course, right? So it's not defined. Okay, but And as you can see that for here, so this is a point that it's pi over 2 here. Okay. So this is a single point. Okay. And so for here, pi over 2, and 3 pi over 2, so that pi over 2 here is another single point. And you have a lot, right? So this next time here, this one is 5 pi. Okay. All right, and so approachingly, we have 2n minus 1 pi for n from 1, 2, 3, etc. So we have infinitely many single points. Okay? Things all right, so they are, so this, and this sequence of points approach to 0. Okay, approach to 0. So that it's not isolated. Why? Because for any neighborhood of 0, so no matter how small it, okay, no matter how small it is, right? You can't find a neighborhood, right? Because for every neighborhood, you have infinitely many isolated points there. So that you can't find a neighborhood such that f of z is analytical except 0, right? Because you have infinitely many points in the neighborhood such that f of z, all right, is not defined there. Okay. So that but at every neighborhood there is a point, right? There is a point that f of z, this tangent over z, this complex function is analytical, because that is still a discrete point there. Okay. So you have singularity, of course, okay, but it is not isolated. Any questions? Okay. All right. Now, if z0 is an isolated singular point of a complex function. All right, so we consider a situation that we have a point z sub 0, which is an isolated single point of a complex function f of z. All right, defined in an open set. Okay, so we have omega here. And so this function is defined in an open set. And of course that this open set so this open set does not include this. Okay. And this is Z0. Right? So Z0 in here and the Z0 at this point may not be in omega. Okay? If Z0 is not in omega, then of course this region, right, is still an open set. Right? So suppose we have this situation. We exclude this point, right? Then a converse function then f of z is analytic in a punctured neighborhood of Z0. In omega. And by theorem 16.1.1, Fz has a Lorentz series expansion about z equal to z0. Okay, so that's okay for all and this is the definition of isolated single point, because that Fz is analytic in a neighborhood of Z0 except the center, right? Except this Z0. So that f of z is analytic in a punctual neighborhood, right? And this punctual neighborhood is in the open set. Okay. All right, and so this is a special type of, as we know, this is the open annual. Okay. So this is an open annulus, right? And right, so that it has Lorentz series expansion like that. And it is clear that beta which is the lim sup of the nth root of the absolute value of coefficients of negative power, okay, it's equal to 0. Okay. Now we look at the negative power series. Okay, so we look at the negative power series. So this is minus n, and z minus z0 nth power. Okay, so now we look at the negative power series. This negative power series, all right, is called the principal part of f of z at the isolated point z equal to z0. Okay. Now, a special case is that if the principal part has only finitely many terms, i.e. the principal is this one, is c minus m not equal to 0. Okay, so that when n is greater than m, that all the c minus n are zeros. But for some m, right, this coefficient is non-zero, right? This coefficient. So the principal part becomes to a sum of finite many terms here. Okay. Now in this case, then z sub 0 is called a pole of order m. Okay, so that the biggest negative power would be minus m, right? So that, and so this isolated single pole will be called a pole of order m. And a pole of order 1 is called a simple pole. Now, and the other case, and if the principal part, so if the principal part has infinitely many terms, okay, then f of z is said, all right, to have an isolated essential singularity at z equal to z0. Okay. All right. So by looking at the number of terms in the principal parts of an isolated singularity, okay, we classify isolated singularity into two categories. One is that poles, okay, the other is called isolated essential singularity. And they have a different behavior geometry. The first is about pole behavior of a pole. Okay, so if a complex function, okay, f of z has a pole at z equal to z0, then the magnitude of the function will goes to 0 as z goes to 0 in any way, in any manner. Okay. So that it will blow up, okay? Blow up, okay? So that is 0. So we have a simple pole, and this is epsilon. Okay. So you can see that if the epsilon is go to 0, okay. So if the neighborhood go to smaller and smaller, this is epsilon prime. Okay, so if epsilon goes to 0 here, now the function value, right? As we know that this complex function is analytic, right? In the punctured neighborhood, means that the f of z is analytic at every point in a neighborhood except the center, right? Except the center here. Okay, and the behavior is that if epsilon goes to 0, right? If we think this neighborhood, then all the points except the center, the magnitude will goes to infinity, right? All right, they will goes to infinity simultaneously. Okay, so that the behavior is that they will go up. Okay, so that is the behavior of the pole. But for isolated essential singularity, then we have Picard theorem, which is called the Picard theorem. Right? Which says that if a complex function f of z has an isolated essential singularity, right, at z equal to z0. Then this function, it takes on every value with at the most one exceptional value in an arbitrary small epsilon neighborhood of z0. Okay. So the behavior, so for the if z0 is a pole of f of z, then we have when z goes to z0 goes to infinity. Okay, so that but if z0 is a pole, it's an essential, it's an isolated essential single point of f of z, then for any A in C, but possibly A0. Okay? That there exists a point z in the neighborhood such that f of z is equal to A. Okay. Okay. All right. So for any neighborhood, right, the behavior of the function f of z, the f of z can be any complex valued, right? So the range will be the whole complex plane except one possible value, except at most one exceptional value. Okay. Usually this exceptional value is 0, but I just say. Okay, so that so in any epsilon neighborhood, okay, the behavior of f of z, right, can be arbitrary. Okay, can be arbitrary. They can have any value. So you can select A from the complex plane, right, except one possible value A0. That you can always find a z, right, in the in an epsilon neighborhood of z0, all right, such that f of z has value a. Okay, so this is called the big Picard theorem. Okay. It's very odd, right? It's very odd, very strange. For Paul, that's fine, right? Because that the magnitude of the value, the function value, will go up to infinity as z goes to 0. Okay, this is the idea when we have the idea of Paul. But if we have isolated essential singularity, okay, then the behavior of fz at even at a very small neighborhood of z0, even epsilon is very small, very small. Okay, maybe very tiny, right? But f of z, the behavior f of z in this very tiny neighborhood, right? The function value can be arbitrary complex number, which may be very big, all right? Except one possible point, one possible value. All right, so any questions about the behavior of Paul and the behavior of isolated essential single points? Okay. Stated in the big Picard theorem. Yes. A0. Okay, cannot be A0, but except A0, it can be any, the value can be any complex number. Okay, for every function you can, it may be possible you have one exceptional value, which we call A0. Okay, so A0 here. Okay. The same value is A0 here. Okay. And except that any complex number can be the function value of a point z in the neighborhood. Even the neighborhood is very, very small. Okay. Any questions? All right, and a complex function f of z is said to have a removable isolated singularity at z equal to z0, right? Because for an isolated singularity, the function f is analytical, it's very well behaved, right? Because it's analytical in a neighborhood of this z0, right? Except the center. Okay. So in some case, we can remove the singularity. So we say that have a removable isolated singularity if f of z is not analytical at z equals z0, but can be made analytic there by assigning a suitable value f of z 0 at z equal to z0. And a very famous example is the sinc function. So the complex function f of z defined to be z and the sine z. Of course, which has an isolated, okay, so which has an isolated singular point at z equal to 0, right? Which is not defined at z equal to 0, okay? So, and it's isolated because that except the 0, in a neighborhood of the 0, right? Other than 0, is other than the center, that this function is analytical. Okay, it's analytical. So, and so this function, which has an analytical, okay, becomes analytical at z is equal to 0 if we define. So if we redefine that f0 equal to 1. Okay. So we define a value for this singularity. Okay. But originally that with this formula, okay, so this we cannot define this function at z equal to 0. Right? But if we redefine f0 to be 1, okay, so the definition is here. And 1. So we will define a function we call tilde. Okay, so we define a function here. So this function is different from this function. Why? Because this function is domain. Its domain is here. But the f tilde function has domain which is equal to the whole complex plane. So they are different functions because they have different domain. Okay? But with that, then this f tilde function becomes to analytical, right? To be analytical at z equal to 0. Okay. So this is about okay, so the isolated singularities are very important, okay? They are very important. And the non-isolated singularity is a little bit troublesome. Okay? So we have to study them carefully, but when we have isolated singularities, as we classify them into two classes, one is called poles, the other is called isolated essential singularities, right? And they will have different behavior, right, around the singular point. For a pole, then the function value will go to infinity, right? The magnitude, infinity, as z approach to z0. But for isolated essential single point, around this single point, that even though the neighborhood is very small, the function will have a value, okay, with arbitrary value, except one possible value, that So so the behavior is very chaotic. I mean, for isolated essential singularities. All right, now zeros. Okay, a zero of an analytic function f of z defined on an open set is a point. It's a point z0 in omega such that f of z0 is equal to 0. Okay, so 0 is a point such that the corresponding function value is 0. Okay, so is that. And a 0 all right, and because fz is an analytic function, all right, on an open set, so as we know, an analytic function is representable by power series expansion, and we know okay. So now, so f has its derivative at z0, right? And so a 0, z0 has order m if its case derivative at z0 is 0 for all k from 0 to m minus 1, but for the m's derivative, right, it's non-zero at z sub 0. Okay. That's the power series expansion of f of z at the point z equal to 0 becomes to n from m to infinity. Okay, so that it started from, so this is becomes to m's power, and okay. So if z0 is a 0 of order m, then its partial expansion of f of z at this point becomes to here. Okay, so it has a factor which is the m's power of z minus z0. Okay, it has a factor here. Okay. Right? Now, a first order 0 is called a simple 0. Right? Just like pole of first order called simple pole. Right? So 0 of first order is called a simple 0. And a 0, okay, which has f of k, z0 equal to 0 for all k greater than equal to 0, right? It's called an essential 0. Okay, it's called an essential 0 here. So essential A0 must be very special. Okay, essential 0 means that if Z0 is essential, then the power series, because that they are all 0. So this is a 0. So you can see that so from this one, a consequence to have an essential 0 is that f of z is 0 for all z in a neighborhood of z0 in omega. Right? So that so this is okay. All right. So this is the power series expansion. So this expansion is good in a neighborhood, right? Which is contained in omega. Okay, as we know in chapter 14, that this is because that f of z is analytical on an open set. So we have that, and if all the f of n are zeros, so that f of z will be 0, okay, in a neighborhood, right? So to have an essential 0 is unusual, which means that the analytic function is 0 in a neighborhood, right, of this essential 0. Okay, and so now we can characterize essential 0 in a domain, right? So f of z, an analytic function okay, on a domain. And remember, a domain is an open connected set, right? Now if fz has an essential 0 in D, then f, the function, is equal to, is all 0 on D. Okay, not just a neighborhood only. The function will be 0 for all points in this domain. The reason is because for a domain is an, so we know a domain is an open connected set. Okay, so we have this behavior. Right, so this is essential 0. Now, the other type of 0 are 0 of finite order, right? So now we will have a theorem to describe finite order zeros, right, are isolated. Oops, sorry. So finite are isolated. So they say that the zeros of finite order, okay, of an analytic function f of z on an open set are isolated. The meaning is that each of them, so each 0 of finite order has a neighborhood, right? Has a neighborhood which contains no other zeros of f of z. Okay, so the situation is here. So this is omega, and there is a 0 here called z0. Then we will have a neighborhood. Then we will have a neighborhood. Okay. So here, f z a 0 of order m. Okay. Then f of z will not equal to 0 for all z in the punctured. Okay, so we can find a neighborhood, right? And when we puncture the center, because this center corresponds 0 is a 0 of order m, right? Then for other z here, the function value will be non-zero. Okay, so the behavior of the function in this neighborhood would be all the function value will be non-zero except the center. Okay, so this is saying that this zero has been isolated. Okay, so final order zeros are isolated. Okay, but essential zero is not isolated, because we know if we have an essential zero, then we have a neighborhood of this essential zero such that the function is all zero in this neighborhood. Okay, so that all the points in this neighborhood are zeros. Okay, are zeros if we have essential zero. Okay, if we have essential zero. So and especially if the function is analytic on a domain, then the whole domain, then the function will be zero on the whole domain. If the function has an essential zero in this domain, only one essential zero, give us that this is zero. Okay, so that is a very different behavior we can have geometrically. Okay. Non-constant analytic function. Oh, okay. Maybe before introduce that concept, I need to. All right. So E. So let E be a subset of the complex plane. Okay. Now a point Z0 in the complex planes is called a limit point. Or sometimes called accumulation point, or sometimes called a clustering point. Of E. Okay, so a point in the complex plane is called a limit point of this subset E if every neighborhood of Z0 contains a point of E different, all right, from Z0. Okay, so okay, so consider okay, so consider E, which is, all right, so there are points here. So this is the complex plane here, And so you can see that 0, z equal to 0 is a limit point, okay, of E. Why? Because the 0, if you take any neighborhood of the 0, so if you take any neighborhood of the 0, you will see that at least one of the point in E is in this neighborhood, right? So for every neighborhood of the origin here, it contains a point of E, okay? Because 1 over n will approach to 0, right? Along the real axis, okay? So they will go into this way. Okay. So z equal to 0 is the limit point of E, okay? But z equal to, no matter how small, for example, but any z in from 0 to 1, okay, is not a limit point of E. Okay, so if you take a E anywhere, I use minus 0. Any z except the origin is not a limit point of E. So this set has only one limit point. And you can see this limit point is not in E. Okay, so limit point of a set, of a subset, may not be in the subset. Okay, right, so they have limit point. If E is a finite set, then E has no limit point. Okay? Because if it had only finite set, then it's impossible because they have distance, right? So here, so suppose this is A1, AN, A1, A2, AN. And you take delta to be the minimum of the distance of A. I. Okay? So you take a distance. And in the whole complex plane. Okay? Right? For example, AY, you can take right, and this epsilon. So the epsilon is delta. Okay, then this neighborhood will not include other points, right? And also, as a limit point, you see that even so it cannot, so any neighborhood can of A1 cannot contain other points, right? Because we say we have to see that different from Z0, right? So even though the neighborhood contain the center, but this A1 does not count into, right? So we find a neighborhood which, except the center, it cannot contain any other points in E. Okay. So if E is a finite set, then E has no limit point at all. Okay, no limit point. Okay. For other X here, you can find a small small neighborhood which does not contain any A sub i's. Okay. All right. So if E is a finite set, then E has no limit point. Right. So that if E has a limit point, then E is an infinite set. So only infinite set can have a limit point. Okay? And just like here, this set is an infinite set and it has only one limit point. Okay. Non-constant analytic function cannot have many zeros. Okay. So we say f is an analytic function on a domain D. So D is the domain and the f is an analytic function on this domain. And the Z is the set of all zeros of f of Z in the domain. All right. So now if Z has a limit point in D, okay? So if Z has a limit point, means that Z must be an infinite set, right? Z must be an infinite set. But of course, an infinite set may not have a limit point. For example, right? So E has no limit point. Okay, because all the integers, right? All the integers in the complex plane, they are discrete point. So that each integer can be isolated. Okay. All right. So this set has no limit point in the complex plane. So even though this set is an infinite set, right? The set of all integers, right? It is an infinite set, but it has no limit point at all. Okay? So of course, if a set has a limit point, then it must be an infinite set. But an infinite set may not have any limit point. So that is so you have to know that. Okay? You have to know. So if you have infinite many points, then but oh, by the way, maybe I will I'll give another here. But a very interesting thing is that a bounded infinite set. Okay, so a bounded infinite set E has a limit point in C. But if the infinite set is bounded, okay, then it has a limit point. This is called the Borano-Weierstrass theorem. Right, this is the Borano. Okay, it's the BW theorem. Okay. All right. So if we have an infinite set, but it's also bounded, right? So this set, why this set has no limit? Because this set is unbounded, right? Because but if we have a bounded infinite set, then this set has a limit point here. All right. All right. So this set, if this set has a limit point, okay, which means that Z is an infinite set, then F okay, then the function is 0. It's all 0 function on this domain. All right, so you compare with this theorem. The theorem says that if we have an analytic function defined on a domain, right, the same. Now, if this analytic function has an essential 0 in D, then of course this is 0. A counterpart here is that even though we don't have essential 0, but if we have a 0 set, if the 0 set has a limit point in D, then we have the same conclusion. Okay, we have the same conclusion. So that there is a very good theorem to have called identity of two analytic functions on a domain. Okay, so if we have two, they are analytic function. right? So suppose we have two analytic functions f and g, right, on a domain. Okay. And if the set, and we want to know whether they are equal to each other, okay, in the domain, then a sufficient condition is here. We look at, we first find so if we find the set, this set has a limit point in the domain, then then they are equal. Okay. So an application all right, so example, we know that cosine square x plus sine square x equal to 1. Okay, so we know this identity. Now, to prove that cosine square z plus sine square z equal to 1, right? So we want to show this identity can be extended to the whole convex plane, all right? So we let f of z to be cosine square z plus sine square z, and the g of z equal to 1. Okay, for all z in the convex plane. Now, since R is contained in all z such that okay, now we know if z is a real number, then these two functions are equal, right? From this identity, right? So that the set of all real number is contained here. Okay, so that the whole real line is contained in this set. Right, so the whole real line. Okay. And okay, and the 0 is a limit point of R, right? Because that the 0 is 0. If you consider arbitrary neighborhood, you see that any neighborhood of the 0 contain a point of the real line other than the center, right? Because that there are many points here. Okay. So 0 is the limit point of R. Okay, and then, so this implies that 0 is a limit point of this set. Okay. Now by this theorem, because this set has a limit point, okay, and so Fz is equal to Gz in C. And the C, as we know, is a domain. The whole compass plane is a domain. It's open connected. Okay. So so this is saying that cosine square z plus sine square z is equal to 1 for all z in C. Okay. All right. So this theorem, because it gives us a sufficient condition to have two analytic functions defined on a domain to be equal on the domain. So an application is to establish identities. So if we have identity in the real domain, right, in real line, then this identity can be extended to identity, right, in the compass plane, right? Usually, if it defined on a domain, right, of the compass plane, okay? So you can extend them, just like this example. Okay. The next theorem concerns about poles and the zeros. Okay, so now if a complex plane, a complex function f of z is analytical at c equal to z0 and has analytical at z equal to 0 means that f is differentiable in a neighborhood of z0, right? In the whole neighborhood. So it is analytical in a neighborhood of z0. That is the meaning of analytical at the point. And has a 0 of finite order. So say m's order at this point. All right. Then 1 over f of z. So we take the reciprocal. This reciprocal has a pole of all m's order. Okay, at z equal to z0. Okay, so the reciprocal is also has isolated singularity. Okay, at z equal to 0, and this is isolated singularity is a pole, right, of the order m's order, and the m the same as the m here. And so that this ratio provided that h of z is analytic at z equal to z0 and h of z0 is not 0. Okay, so you turn a 0 of finite order to a pole of finite order of the same order, right? Conversely, and if a complex function f of z has a pole of mth order at z equal to z0, then, and we know poles are isolated, okay? I will show. Then 1 over f of z, okay, is analytic at z equal to z0 and has a 0 of mth order at z equal to z0. And so does h of z divided by f of z, provided that h of z is analytic at z equal to z0 and h of z0 not equal to 0. All right, so this theorem gives us, by taking the reciprocal, you turn a pole to 0 with the same order, and you turn a 0 to a pole. Okay, so that this is quite essential. Now right. So you can see from our previous discussion that we may face up functions, right, which is analytical in some open set, but maybe singular at some points. Okay, right. So this function are important in our applications. So so we will give this function a name. So a complex function f of z is said to be meromorphic in an open set. All right, so we say meromorphic in an open set. If there is a subset A of omega such that 1, A has no limit point in omega. So A has non-limit point, means that either A is a finite state, or, so which is says, this is saying that either A is a finite state, or A intersect with the disk. All right, it's a finite set for all n. Okay. Well, so together, I think maybe I just use an equivalence says that A intersect with D is a finite set. Okay. So A has non-limit point means that if you consider bounded okay, the point of A will be finite. Okay, so that within a ball or a disk, you can't have infinitely many points in A. So this point should be scattered around. Okay, scattered around. Even though A may be infinite, but in a bounded state like this disk, that A can have only finite many points in this disk. Okay, right. This is the first thing. The second is that H is holomorphic. Okay, in omega except points in A. And third thing is that Fz has a pole, okay, at each point of A. So at each point of A, F has isolated the singularity. All right. Okay, and which is not essential, so that they have poles. So they have poles. Okay. All right. So any complex functions, all right, has these properties, what we call meromorphic functions. Okay, they are so that so f of z is analytic in omega, but minus A. Okay, and at each point of A, f has a pole. So that means that in a neighborhood of any point of A, f is analytic. Okay, except the point. And this point is an isolated single point. Okay. All right. So this is called meromorphic functions. Wow. All right. So time flies, you see, very quick. and it's approaching to the end of the semester. All right. So now, with about 15 minutes, I try my best to introduce you the concept of residue, because the residue integration method is one of the brilliant parts in complex analysis. All right, so we consider f of z. All right, so f is a complex function, which right. So consider right. So consider a complex function f of z, okay, which has a pole over an isolated essential singularity at z equal to z0. Okay, so so basically, the f of z has an isolated singularity at z equal to z0. Okay, and this isolated singularity may be a pole or an isolated essential single point. All right, and so we let qz to be its principal part, as we defined previously. Okay, so this one, the principal part, okay, of f of z at this single point, z sub 0. All right, and consider gamma. So gamma is a cross path. Okay. In the complex plane with the single point z0 is not in the image of gamma. Okay, so that the cross path. Okay, so this is gamma star here, and and we have z0 here. Okay, so we have z0 here. Now, so that gamma star, as we know, this is a compact set. Okay, so this is a compact set in the complex plane. So that means that, and so if we define f of z to be z minus z0, okay. Now this is a continuous function on gamma star. Okay, so the distance function, right? It's the distance function is actually a continuous function, okay, on the star, continuous function. So the image, okay, is also a complex set. Okay, so it's a complex set in R, and so that there exists D1 and FZ and the D2 for all, so that there exists D2 greater than equal to D2 and right, such that for all Z in gamma star. Okay. Because the continuous image of a complex set is also compact, okay, so that a complex set in R is a bounded, so has the maxima and the minima, okay, right? And so we have D1 and D2, okay, so that we are able to so this is D1 and to touch here, and you have this is D2. So there exists D1 and D2. Okay. And the distance in between them. So this shows that so so there exists such that gamma star is in the annulus and the D1, D2, okay, and the closed bar, including the boundary. Okay, so the whole image of the cross curve will be inside here, will be inside this one. So if we have that, then the gamma is contained in in the annulus of okay. Now, since the Lorentz series right, so look at the principal part. So this principal part is the Lorentz series. Since the Lorentz series okay, has convergent open annulus, okay, which is A, Z0, 0 and infinity. Okay? So this Lorentz series has convergent open annulus. Since the alpha is the lim sup and the coefficient of all positive power is 0. 0. So this is 0. So this says that infinity. So that's why we have infinity here. And the 0 is because that it has a pole. So in a neighborhood of Z0, f of Z is analytic. Okay, so that's why it is 0 here. Okay. So as a pole, it has a neighborhood. So f of Z is analytic at the punctured disk. So that's why the beta is 0. Okay. Otherwise, if beta is not 0, then it should diverge, right? But reality is that except Z0, all the point, all right, this Lorentz series should converge. Okay. Okay. So this Lorentz series has convergent open annulus. Okay. This is this one. Since Z0 is a pole of finite order, or just a pole means a finite order, okay? So it's just a pole, okay? So when it's a pole, we have that. So this is the situation. Okay, and so that's this Lorentz series okay, well, converges uniformly in the closed annulus. R1, R2 by theorem 16.1.c. I think this is from, no, it's not this one. So, and because gamma star is a subset, I think this is from 15.5.3, I think, because we consider uniform convergence in section 15.5. I forget the number. Oh, yeah, that would be 16. Yeah, because we have dual extension. Sorry, 16.1.c. That's correct. Okay, I'm sorry. And so that this is Lorentz series. Converges uniformly. Okay, so this converges uniformly in gamma star, because gamma star is in this closed annulus. Okay. All right, so with uniform convergence, now by theorem 15.5.3, now the integral gamma of the principal part so this is all right. So it is the integration of a serial sum, and the summation can be by z. Now, so now we can exchange the integration and the serial sum operation. Okay, so this sum is there. But as we know that it's 0 for all n greater than or equal to 2. And we know it's 2 pi I times the index of gamma is 0. Okay. Right? So we have this one. So for n greater than or equal to 2, this integral is 0, as we have known in the chapter 14. But when n equal to 1, this is just by definition of the index is 2 pi I times the index of z. So that we finally has the principal part. This comes to c minus 1 times the index gamma of z0. Okay. And And C minus 1 will be called the residue of f of z at z equal to z0, right? And sometimes denoted as to be, so that it will be denoted as res z equal to z0 of f of z. Okay. So that is the integration. Okay. Okay. So I think I have to stop here. And you have to read for the rest of the lecture notes.